Today, our topic of discussion is elements, atoms, molecules, and chemical bonds. Now, in this lecture session, we'll discuss the constituent of matter, that is atoms, and their structure and properties. Also, we'll discuss the capacity of the atoms to combine with other atoms to form molecules. And lastly, we'll consider how matters change by chemical reactions. Now, all matter is composed of atoms. Now, each atom consists of a dense, positively charged nucleus around which one or more negatively charged electrons move. So, this is the so-called Bohr model of a helium atom. In the center, you have the nucleus, which contains protons which are positively charged and has a mass of 1, and a neutron which is electrically neutral. It also has a mass of 1, and surrounding the nucleus negatively charged electrons are rotating. Now these electrons, they are negligible in mass compared to the mass of proton or neutron. See, proton has a mass of 1.7 into 10 to the power minus 24 gram, which is equivalent to 1 Dalton. Same for neutron. But for electron, the mass is almost 10,000 times less than that of a proton or neutron. Now the nucleus, though it contains almost the entire mass of an atom, it occupies only 10,000th fraction of the volume of the entire atom. Okay, so this picture is an exaggeration of its volume of the nucleus. But though electrons, they are considered to be negligible in terms of mass, but they are the deterministic factor for the atoms, how they will combine with other atoms to form stable associations. Now, element is a pure substance composed of only one kind of atom. Okay. Now, there are more than 100 elements in the universe. About 92 of them are naturally occurring and the rest are prepared in the laboratory. And all these elements, they have been organized based on their physical and chemical properties in the so-called periodic table of elements. Okay. So, this is a representation of the periodic table of elements. Now, in this picture, you can see that some elements have been highlighted with yellow. Okay. So, these are the elements, the 6 elements: hydrogen, carbon, nitrogen, oxygen, phosphorus and sulfur. They are biologically most abundant. Almost 98% of a cell, any living cell, is composed of these elements. The other elements that have been highlighted in orange, they are also biologically important, but they are not that abundant as the other 6 elements. Here, the biological roles of these elements have been summarized in this table. For example, the 6 major biological elements, hydrogen, carbon, oxygen, nitrogen, phosphorus and sulfur, they are the components of the major biological molecules. Potassium, sodium, chlorine, they produce electrolytes and they are responsible for fluid balance and nerve transmission. Calcium, magnesium, zinc, they form bone structure as well as important for nerve function. Zinc, strontium, iron, copper, cobalt, manganese, they are essential trace metals in human metabolism. On the other hand, these metals, cadmium, mercury and lead, they are considered as heavy metals and they are toxic to living cells. Now, this is a representation of a typical atom where a chemical symbol is given to the atom. In this case, the example is taken is helium. Now, each atom of any given element has a distinguishing number of protons that sort of characterizes that atom, and that number of protons in that nucleus is called the atomic number. Okay, say in helium, you can see in the nucleus there are 2 protons, so its atomic number is 2. On the other hand, there is another term called atomic mass or mass number, which represents the total number of protons and neutrons in the nucleus. Okay, in helium there are 2 protons and 2 neutrons in the nucleus, so the mass number is 2 plus 2 or 4. That is 4. Now this is the typical symbolic representation of an element. So what you do is you write the symbol of the element, and in the left superscript you write the mass number, and in the bottom subscript you write the atomic number. Okay, like hydrogen is written like this. So 1 is the atomic number and 1 is also the mass number, because hydrogen nucleus does not contain any neutron. For carbon it is 6 and 12, that means 6 protons and 6 neutrons. In oxygen it is 8 and 16, that is 8 protons and 8 neutrons in the nucleus.
Sir, are atomic number and atomic weight the same?
Technically not exactly same. To understand that, we need to consider the concept of isotopes. Let's see, there are some elements where the number of neutrons may differ. Okay, the number of protons will be the same, but number of neutrons will be different. These are called isotopes of the same element. They are same because element is distinguished by the number of protons in the nucleus, which is same, but the neutrons different. Let us consider the case of hydrogen and its isotope. In the normal hydrogen, you see there is only one proton in the nucleus. In the isotope deuterium, there is one proton and one neutron. Okay, and in the isotope tritium, there is one proton and two neutrons in the nucleus. So this is a case where isotopes of same element have different names, but other elements which have isotopes like carbon, nitrogen, oxygen, phosphorus, sulfur, they do not have distinctive names for different isotopes. Now atomic weight, or which is also called atomic mass, is the average of the mass numbers of the different isotopes present for the element, taken into account their relative abundance. Consequently, these type of average values can become fractional. Okay, for example, the atomic weight of hydrogen is 1.0079. On the other hand, atomic number is always integral. For hydrogen it is 1. Okay. Now biologists, they are usually very much interested in studying the chemical changes that occur within the cell. Okay. And these chemical reactions, they alter the atomic compositions of the substances and thereby their properties. Now these type of chemical changes within the cell, they usually involve changes in the distribution of electrons between the reacting atoms. So to understand these reactions, we first need to understand the organization of electron within an atom. Now a Bohr model kind of took a simplified view, or assumed a simplified view, that electron is a particle and it moves around an orbit, a defined orbit around the nucleus. Consequently, its location can be pinpointed at any time. But in reality, electrons actually occupy a space around the nucleus within which the probability of finding the electron is very high, like 90% of the time. And that region of space is called an orbital. In this way, the concept of orbital is radically different from the concept of orbit. Now, orbitals can be different shapes and different orientations, like the s orbital, which is spherical, or the p orbital, which is dumbbell shaped. Okay, but whatever be the nature of the orbitals, each single orbital can occupy maximum number of 2 electrons. So either the orbital can be totally vacant, 0 electron, or 1 electron can be there, or at maximum 2 electrons can be there. There is a concept called electron shell around the nucleus, which denotes the energy level around the nucleus, which could be occupied by the orbitals. Okay. For example, closest to the nucleus is the first shell. So the orbitals within the first shell will have the lowest energy. After the first shell, a little bit farther from the nucleus, there will be the second shell. Okay, so the orbitals occupying the second shell will have higher energy. And then you have the third shell, so the orbitals in the third shell will have even higher energy. So when the electrons will occupy the orbitals, they will occupy depending on the energy of the shells. The lower energy shells will be occupied first, and successively the higher energy level shells will be occupied. For example, the first shell contains only one s orbital. Okay, so only 2 electrons can occupy the first shell. When 2 electrons occupy the first shell, it is totally filled up. Then comes the second shell. In second shell, there can be 4 orbitals, one 2s orbital and 3 p orbitals. So after the first shell 1s orbital is filled up, then successively the 2s orbital will be filled up by 2 electrons, and then the 3 p orbitals will be filled by 2 electrons on each. So to completely fill up the second shell, you need 8 electrons because there are 4 orbitals. So 4 into 2, total 8 electrons will be needed to completely fill up the second shell. The chemical reactivity of an atom is determined by the occupancy of the outermost electronic shell. The reason is that if the outermost electronic shell is completely filled, then the system is stable, so it will not try to react. On the other hand, if the outermost electronic shell is incompletely or partially filled, that's an unstable situation. So the element will try to react in a way so that its outermost orbital is completely filled. Consider the first shell elements, hydrogen and helium. Okay, their outermost shell, that is the only shell, is the contains only the 1s orbital. In hydrogen, there is only 1 electron, so it is partially filled and reactive. But helium contains 2 electrons in its orbital, so it's filled up and it is stable. It's sort of inert. In the second shell elements, you see that the outermost orbital will be filled up by 8 electrons. So all these elements, lithium, carbon, nitrogen, oxygen, fluorine, they all have partially filled orbitals, the outer shell orbitals. Consequently, they are reactive. On the other hand, neon has all the 8 electrons that are filled up their outermost shell. So neon is stable, non-reactive. Same goes for the third shell and on. Now, hydrogen or helium, the first shell elements, they are stable if their outermost orbital contains 2 electrons. So hydrogen will react in that way so that it can achieve 2 electrons in its outermost shell. On the other hand, say carbon or nitrogen or oxygen, they will try to react in a way so that their outermost shell will contain 8 electrons and they are completely filled and the element gets stability. So this is called octet rule because 8 electrons are needed to stabilize the system. Now many elements in the periodic table, they follow this octet rule while they undergo chemical reactions. Now atoms can be linked with each other to form molecules. This link is termed a chemical bond, which is an attractive force that holds the 2 atoms together in a molecule. Now, these chemical bonds can be of various types. For example, covalent bond, which results from sharing of electron pairs. And under physiologic condition, that is in presence of water and a particular pH and ionic strength, the bond energy of a covalent bond can range from 50 to 110 kilocalorie per mole. So it is quite strong. Then there are ionic bonds that result from attraction of opposite charges. But under physiological condition, the bond energy is quite low, 3 to 7 kilocalorie per mole, but still quite significant. So other than these two, there are 3 other different types of bonds that are biologically important. For example, hydrogen bond, hydrophobic interaction, and van der Waals interaction. Now, this picture kind of explains how a covalent bond is formed by sharing electrons. Say a simple case, 2 hydrogen atoms are bonding with each other in a covalent manner to form a hydrogen molecule. See these 2 separate hydrogen atoms. These are their nucleus around which you have the electron in the orbital. Now this nucleus is attracting its own electron. But when the two atoms have come a little bit closer, then the nucleus can also attract the electron of the other atom. And similarly, this nucleus will attract the electron of this other atom. Consequently, the orbitals will be distorted in this way, and they will be even drawn closer together. And then eventually, the two orbitals will overlap, and consequently, the two electrons which were initially separate, now they are sharing the same overlapped orbital. Consequently, each atom is enjoying these two electrons. Okay, and since, as you can see in this Bohr model, for hydrogen, the outermost shell is filled up when there are two electrons, and that gives maximum stability. So after the covalent bond formation, you can see each hydrogen atom is having two electrons for themselves. So it's a stable system, and that's how a stable covalent bond is formed. Similar covalent bonds can form between atoms of different element, okay, two or more, in a specific ratio. In that case, the kind of molecule that are generated, we can call them a compound. For example, methane, CH4, between carbon and hydrogen, water, between hydrogen and oxygen, then the table sugar sucrose, between carbon, hydrogen and oxygen, in a particular ratio in each case. They are chemical compounds. And here you see that, say in case of methane, one carbon atom has formed covalent bond with 4 hydrogen atoms by electron sharing. And after the electron sharing, you can see each hydrogen atom has completely filled outer shell, because each are having 2 electrons in them, so they are stable. And the carbon atom is also stable, because now it has 8 electrons in its outer shell. So according to octet rule, it has attained stability. So in this way, the compound is a stable compound formed by covalent bonds. The geometry of the covalent of these type of covalent molecules can be expressed by this ball and stick model, where you can see that the hydrogen atoms are arranged around the carbon in a tetrahedral manner. Okay, that depends on the orientation of the overlapped orbitals of carbon and hydrogen. In this space filling model, you can see this represents the overall shape or contour of the molecule.
Sir, is the electron pair in covalent bond shared equally between the two atoms?
Not always. That we can understand if we look at the concept of electronegativity. See, each nucleus exerts an attractive force towards a bonded electron pair in a covalent bond. Okay, and that attractive force is called electronegativity. Now, more the positive charge of the nucleus, depending on the number of protons, more will be the attractive force, or less the distance between the positively charged nucleus and the bonded electron pair, more will be the attractive force. Okay. So, if the two atoms that have formed the covalent bond and shared the electron pair have similar or same electronegativity, then obviously both will pull the electron pair in a similar force, so the electron pair will be shared equally between them. These type of bonds are called non-polar covalent bonds. But if the electronegativities of the two participating atoms are different, then the one with higher electronegativity will exert a greater force for the electron pair. Okay. Consequently, the electron pair will be shifted towards this atom a little bit more compared to the other atom. Okay. And consequently, the electron pair will be unequally shared. These type of bonds are called polar covalent bonds. Okay. Here there is a list of electronegativity values of different elements. They are dimensionless quantities. So oxygen is highly electronegative, so is chlorine and nitrogen. On the other hand, sodium and potassium, they are much less electronegative. And these elements like carbon, phosphorus and hydrogen, they have intermediate values of their electronegativities. Now, if the electronegativities of the interacting atoms are very different, for example that of sodium and chlorine, then the atom with higher electronegativity can abstract or steal one electron from the other one. Like in this case, if sodium and chlorine come close together, then chlorine, because of its much higher electronegativity, can extract an electron from sodium. Now, the consequence of this type of interaction is very interesting. For example, first of all, the sodium, which now has lost one full electron, will carry one complete positive charge. Okay, we call this as an ion, in this case a cation, a sodium cation, Na+, one positive charge. See, now its outer shell has vanished. The inner shell has become the outer shell. The inner shell was already completely filled. It already has 8 electrons. Consequently, sodium ion, that is Na+ ion, is quite stable. On the other hand, chlorine, after gaining one full electron, has now one complete negative charge. So it is another type of ion, in this case anion, Cl-. Now, after gaining one full electron, you see its outermost shell is now completely filled by 8 electrons. So even the chloride ion, the Cl- ion, is also quite stable. And now this Na+ ion and the Cl- ion will attract each other electrostatically, and the result is formation of an ionic bond. Okay. Now, if atoms or molecules, they collide with each other with sufficient energy, then it may so happen that they can combine or they can exchange their bonding partners. This is nothing but the process of chemical reaction. Now, these chemical reactions can be accompanied by release of energy in the form of heat and light, or there are some reactions which absorbs energy from the system. Let us take this example, the reaction of propane with molecular oxygen to form carbon dioxide and water with a release of energy as heat and light, which is seen as a flame when propane burns. Now, here these two molecules, they have collided with each other and exchanged their bonding partners. For example, here carbon was combined with hydrogen. You see, after reaction, carbon has combined with oxygen. On the other hand, here molecular oxygen was free, but after the reaction, the molecular oxygen has combined with hydrogen. So they have exchanged their bonding partners. Now, there are two very important rules of any chemical reaction. First of all, matter is neither created nor destroyed. Here, there are 3 carbon atoms. After the reaction, still there are 3 carbon atoms. Here, there were 8 hydrogen atoms. After the reaction, again you have 8 hydrogen atoms. Here, there were 10 oxygen atoms. And after the reaction, you have 6 plus 4, again 10 oxygen atoms. So mass is conserved. And for energy, also the total energy will be conserved. Energy cannot be created or destroyed, but energy may change its form while the reaction. Okay. For example, here the energy were stored within the molecules as chemical potential energy. After the reaction, a part of this chemical potential energy is released as heat and light. The rest is still stored within these molecules as chemical potential energy. Okay. Today, we have learned some important features of matter. First of all, the composition of matter by atoms. Then we learned atomic structure. Atoms are composed of subatomic particles like electron, proton, neutron. The mass of the atom is almost entirely contributed by the protons and the neutrons in the nucleus. The electrons, though they do not have significant mass, but they are very important for the atom's reactivity. Okay. Then we learned about elements, the different elements present in the periodic table, and we particularly gives stress on the biologically relevant elements and their roles in a living cell. And then we understood the role of electrons in the chemical reactions, that is when atoms react with each other to form molecules. Okay. And further we understood how different atoms and molecules can chemically react with each other to form new molecules, generation of new products. And we also considered the involvement of energy within this system.